In this video, I'm going to show you how to solve a projectile motion problem, and this one is inspired by a scene from The Bourne Identity, in which Matt Damon sprints down a hallway, jumps out a window, and crashes through the window of an adjoining building. If you're into action movies, you can probably think of your own example of a similar scene, but if you want to see this scene for yourself, just Google Bourne Identity window jump and you'll find it. So the question we're going to answer is, what initial velocity is required to complete this jump? And we're going to make an assumption that the initial velocity is completely horizontal. Now, before I go on, I should say that even after you watch this movie and understand how to calculate the minimum velocity, you should not try this jump. Remember, Jason Bourne is a highly trained government operative, and even he used a stunt double for this scene. So please be safe. I don't know the exact distance between buildings or the vertical drop for this jump, so I'm just going to make some estimates based on how things look in the movie. Let's say that the horizontal distance between the buildings is about 4 meters and the vertical drop from one window to the next is 2 meters. Believe it or not, that's all the information that's required to determine the horizontal velocity. So let's put a picture of the problem up in the corner and get the constant acceleration equations up on the screen as well. For projectile motion, we want to remember that the motion may be distilled into what is happening in the horizontal direction and what is happening in the vertical direction. I like to make two columns, one for the y direction and one for the x direction. I like to write down the information there to keep it clearly separated. So in the y direction, the vertical displacement is minus 2 meters. The minus sign there indicates that I've chosen down to be negative. And so when I write down the acceleration in the y direction, that's also down. And so it's negative 9.8 meters per second squared. I estimated that the horizontal displacement was 4.0 meters, and the acceleration in the x direction is 0 meters per second squared. In the y direction, the initial velocity is 0. The final velocity in the y direction is unknown, and the time is also unknown. In the x direction, I don't know the initial velocity, but I'd like to know it. I also don't know the final velocity in the x direction, but I know that it's equal to the initial velocity. I also don't know the time in the x direction, but I do know that the time in the x direction and the time in the y direction are the same. So if I find the time on one side, I can apply it to the other side. All right. So now that I have my columns squared away, I can begin to look at the constant acceleration in conjunction with the information I have and try to figure out the best way to proceed. Now remember, the constant acceleration equations that I have written down here look like they're for the horizontal direction, but if you substitute y's for x's, you'll have equations that work for the vertical direction, so don't be deterred by that. So take a moment and look at the two lists. The ultimate goal of the problem is to find v0x, but you can't get there directly with the information that's currently in the x column. So where do you think we should start? Note that in the y column, we have delta y, ay, v0y. And it's useful to find t because if we find t in the y direction, we can transfer it over to the x column. So looking at the list of equations here, we can use the first one to find time. So changing x's to y's, I have delta y equals v0y t plus 1/2 ay t squared. I've added some y subscripts to really emphasize that I'm in the y direction right now. Making substitutions, I have minus 2.0 meters equals 0 t plus 1/2 times negative 9.8 t squared. The 0 t goes away, and solving for time, we find that the time is 0.639 seconds. Now that time applies here and also applies here. So now I have more information in my x column. So now that we have time, we can go back to the constant acceleration equations and solve for v0x. Take a moment and think about which equation will work for us. Notice that you have delta x, ax, t, and you're looking for v0x. The first equation contains all of these terms, so that's the one we'll want to use. Delta x equals v0 xt plus 1/2 at squared. Making substitutions, 4.0 is equal to v0x times 0.639 plus 1/2 times 0t squared. The last term goes away, and solving for v0x, we find that v0x is 6.3 meters per second. And that's the answer. Okay, so whenever you finish a problem like this, you should take a moment to consider whether the result is reasonable. If you figure that each stride is about a meter, this person would need to make about 6 strides in a second to achieve this speed. Look back at the video clip to see if that's about right. Of course, I've estimated distances and made a big assumption that the initial velocity is horizontal, so don't go too crazy counting strides. Just look at the video and convince yourself that this value is somewhat reasonable. If you want to see an example of a projectile motion problem for which the initial velocity is not horizontal, check out the next video in the series.